Okay, so bipartite graphs and coloring. Bipartite graphs, I think, are in section 8.1 or 8.2. And we don't really do a whole lot of coloring, but I did want to show you an example of how coloring works because it's actually really useful if you're trying to schedule things. So here's what bipartite means is all the vertices can be split into two groups so that all the edges connect a vertex in one group to a vertex in the other group. Okay, so are these graphs bipartite? One way to tell is try and color the vertices, right? And the rule for coloring is any two vertices that share an edge have to have a different color. So the one on the above right, this one is bipartite. If I make this a red vertex, then every vertex it's connected to has to be a different color. So that would have to be a blue one, this would have to be a blue one, this would have to be a blue one. Every vertex that is connected to a blue one has to be red. So that would mean that this would have to be red. And that's okay, it's connected to two blues. This one would have to be red, okay? And these two would have to be red. We haven't run into any problems so far. Everything connected to a red one has to be blue. So this one has to be blue, and it's okay to color it blue because everything it's connected to is colored red. This one would have to be blue. That's okay, everything it's connected to is colored red, except for this one, but everything this one's connected to is colored blue, so this one can be colored red. So that one is bipartite because I can color everything, every vertex a different color, and two vertices of the same color are not connected by an edge, right? Edges connect only two vertices of different color. What about this one? Well, same procedure, right? And this is, again, you know, how to deal with graphs is start at one point and work your way out and hope you don't run into any contradictions. So if we start with E, suppose we make this red, then I'll have to make everything that E is connected to blue. So F would be blue, G would be blue, A would be blue, and D would be blue. And there's a problem. A and G are both blue. And there's really nothing you can do with it, nothing you can do about this. The problem is the three cycle, A, G, E, right? And so this is a subgraph. We'll just take out this thing, right? And if you look at a triangle like that or a three cycle, see that you can't color that with two colors, right? You can't make whatever color E is, if A and G have to be different colors, well, then A and G have to be the same color, and then A and G, it's not bipartite because those are two vertices of the same color sharing an edge, and you can't have that. So three cycles, if you have a three cycle in a graph, you can't be bipartite. So this doesn't have a Hamiltonian cycle, but it is bipartite. And so how does that help us understand what's going on? Why it doesn't have a Hamiltonian cycle? Well, I can take this, I'll call this vertex A, this red vertex in here B, this one C, this one D, E, and F. And I can draw that. I'm going to redraw the graph, but I'm going to draw it in a different shape. So A, B, C, D, E, and F. Vertices a little bigger. So I'm going to draw those red vertices all in a column. And then how many of blue vertices do I have? 1, 2, 3, 4, 5. And so I'll call this one R, this one S, E, U, and V. So we have 1, 2, 3, 4, 5 vertices that are blue, R, S, T, U, and V. And now we just connect everything up with various edges. So A is connected to R, S, and V. R, S, V. B is connected to S, R, and oh, there's one in the center, but I call that T. Okay, good. So B is connected to S, R, and T. So B is connected to S, R, and T. What's C connected to? C is connected to R, T, and U. What about D? D is connected to R, U, and V. What's E connected to? E is connected to V, T, and U. V, U, and T. And finally, F. F is connected to V, T, and S. V, T, S. Okay. So there's a graph of this as a bipartite graph. Note that there's no edges that connect a red vertex to a red vertex. There's no edges connecting a blue vertex to a blue vertex. This graph and this graph, they're different pictures of the same underlying graph. Remember that a graph is just a list of vertices and a list of the edges that connect them. You can draw them in lots of different ways. This way is, if you draw it this way, that points out that you can draw it with no crossings. This way highlights the fact that it's a bipartite graph. And so now you can sort of see what the problem is with having a Hamiltonian cycle. A Hamiltonian cycle should start and end at the same place and should go visit each vertex. But we've got 1, 2, 3, 4, 5, 6 red ones and 5 blue ones. So if we started a red, we can only go red to blue, blue to red, red to blue, blue to red, red to blue. So if we've done 4, so if we start with go A, R, B, S, C, T, D, U, U, E, V. Well, from V, we can go back to F, but then we can't get back to A, right? Because we don't have another blue vertex, so I can connect to that and then go back. Right? So I've got more red vertices than blue vertices, so I can't have a Hamiltonian cycle because I always have to go red, blue, red, blue, red, blue, and I just don't have enough blue vertices to do it. So this particular bipartite graph, because it's bipartite, tells me why it doesn't have a Hamiltonian cycle. So the features of graphs sort of interplay with each other a little bit. So we can generalize bipartite to colors. So a graph is called n-colorable if the vertices can be colored with n different colors so that no two vertices share the same color, and n is the smallest number that this is true, right? Because if you have 100 vertices, you can certainly color it with 100 different colors, right? But you're actually interested in what's the least number of colors you can get away with. So coloring graphs have a number of applications, one of which is scheduling. I have stolen this, borrowed is the technical term, from this website. It's actually a really good example of coloring. So suppose the math department offers courses 112, 115, 221, 222, 271, 325, 327, and 423, and all this other stuff is stuff that I should have cut out. So ignore that. That actually comes from the original thing. And so the table below shows concurrent enrollments, and X means a student enrolled in both courses. And the department needs to schedule final exams. So for this suite of classes, how many different final exams how many different final exam slots do they need? And the problem is, of course, is that a student that's enrolled in 2 different classes the classes can't have the final scheduled at the same time. So how can we deal with this problem? Well, first off, we'll turn it into a graph. We will list all the courses as vertices. 325, 327, 423. So there's all the courses that I've got, and they're all listed as vertices. And we'll put an edge between 2 courses, and an edge means that a student is enrolled in both of the courses. So for 112, 112 has no edges. It's an isolated vertex. none of the students in 112 are taking any of the other classes. What about 115? Well, 115 and 222 share a student, so that gets an edge. What about 221? 221 has a student with 222, so that gets an edge. 221 with 271, so that gets an edge. 221 with 325, so that gets another edge. 221 with 327, that gets another edge. I'm drawing it sort of with big loops because I don't want to have too many crossings. And that's it. So there's the connections for 221. So 221 is students taking a lot of different courses. 222, well, we've already done connections to 115 and 221, so we just have a connection to 327 and 423. 271, we've done the connection to 221, but it should be connected to 327. Oops, sorry. For 271, 221, we've got a connection there, but also to 327 and 423. So 271 should be connected to 327, and now we'll have to cross something. 423. 325, we've done its connection to 221, but 325 is connected to 327 and 423. You have to have some more crossings. And then 327, we've done all those connections for 327, 423, we've done all the connections for 423. Right, 1, 2, 3, 4, 1, 2, 3, I missed one. Fudge. Oh, right, 327 is connected to 423. I missed that. There we go. So there is our graph of courses where each vertex is a course and each edge indicates there's a student taking both courses, right? So it's a scheduling graph. So what I'll do is I'll pick one of these things. 221 seems to be one of the most connected ones. So I'll make 221 blue, right? And that means that everything that's connected to 221 has to be a different color. So I'm going to tentatively make everything connected to 221 black. So that makes 222 black. That makes 271 black. And then 327, I'd like to make 327 black, but I can't make 327 black because it's connected to 271 and to 222. These are both already black. So 327 can't be blue because it's connected to that. It can't be black because it's connected to that. So we need a third color. We'll make 327 red. Okay, and so that deals with everything connected to 221. What about stuff connected to 222? Anything connected to 222 can't be black, but it could be either blue or red. For 115, it doesn't really matter whether it's blue or red. We'll just make it red. 423, though, is connected to 222 and connected to 327, but it's not connected to 221. So I can make 423 blue. 325 is connected to 327, to 423, and to 221. But this one's red, and these two are both blue. So I can make 325 black, and I should have done that a little bit earlier. But that's okay. Great. And 112 is not connected to anything, so it can be colored whatever color you want. And we will make it, we'll make it red. What the heck? So if you look at the three colors that we have, all the colors, all the classes that are red don't share students. All the classes that are blue don't share any students, and all the classes that are black don't share any students. So we can have 3 final exam slots call it red, that's 112, 115, and 327. Blue, 221 and 423. And then black, the other 3 courses, 222, 271, 325. So that's a scheduling problem. I'm not a computer science person, so don't quote me on this, but I think if you're trying to schedule processes within a computer, you have you can't have some sorts of issues, and you can have these sorts of solutions to them. So scheduling problems are often phrased as graph problems.